So we're going to continue with some key observations based on our last exploration of how the straight line solutions in the vector field work. So the first one was along any straight line solution for a system of differential equations. If the straight line solution passes through the origin, the vector field must point towards or away from the origin everywhere along that straight line solution. So we saw that on the previous example, where no matter where you were along that straight line solution, if you were along that straight line solution, everything pointed towards or away from it, right? So the second thing that we can kind of observe and make note of is that the vector field, at any location on the phase plane, any x and y coordinate, if you want to think of it that way, must point in the direction of the origin. Or exactly away from it. If and only if, this is one of those if, IFFs, if and only if that point is on a straight line solution. Right? So it's basically a guarantee that if you have a vector that's pointing at a particular location that's pointing directly towards the origin or directly away from it, then you know you must be on a straight line solution. Right? So if you're on a straight line solution, everything points towards or away from the origin, and if you are just floating around on the vector on the phase plane and you test the vector field and it points towards the origin, then you know you're on a straight line solution. So for example, let's take a look at these two here. When we plug in the point -1, 2, remember these are the coordinates. And when you multiply it by that coefficient matrix, this is the vector field value. So this is the vector field value. And we're going to do a little bit of kind of sneaky manipulation here. And if I factor out a 4, the greatest common factor for both of these, if I factor out a 4, I wind up with something that's kind of interesting. I wind up with this part of it, this vector part of it, that's telling me the direction and the other part of it is this 4 right here, and that's telling me the strength of the vector. So in a way, it's kind of telling me it points in the direction of right 1, down 2, and it does it with a strength of 4. Now, I could have a vector that points in the same direction, but with a larger strength. It's just not going to be at the coordinates of -1, 2. So for the other one, if we have our coefficient matrix times our coordinates of 1/2 and -1, we get this. And if I factor out the greatest common factor here, and I wind up with -2 times this, you'll notice that we have the exact same direction, but with a different strength. So they have the same direction, but a different strength. And that makes sense because at the point 1/2 comma -1, that's not going to give you the same vector field value as -1 comma 2. They're going to give you two different vectors, but because these 2 points are on the straight line solution, so off to the side we can say since -1 comma 2 and the other point, which is 1/2 comma -1, are both on the line y equals -2x, they're both going to point in the same direction. I should say they're vectors. I don't want to say they, I want to say they're vectors. Both point along that direction. So that's a big deal. Again, using our observations from up above. Or in general, we can say, if you have a system, a linear system that looks like this in matrix form, remember A is our coefficient matrix, and remember that y value is really just any x and y coordinate that you want to give it. Plug it in here and you get the vector field value. We're looking for a number, any particular number, that when we multiply the coefficient matrix times it, it's the same as multiplying it by some constant number. Now notice you have this vector field value out here multiplied by a number. So what we're going to do is look for a special number, lambda, that makes this true. And you'll see why here in a minute once we get to the next page here. So this means on the next page, in a generalized way, we've got our coefficient matrix, or the parameters that make up our coefficient matrix, times xy, and that's got to be equal to some lambda times xy. And what we're going to do is we're going to turn that into a system of equations. So a times x plus b times y is equal to lambda times x. That's the first equation. The second equation is c times x plus d times y equals lambda times y. So there's really two equations going on there. This matrix equation represents these two. And so what we can do is we can manipulate these a little bit. I'm going to manipulate those and turn them into this pair of equations. I'm going to subtract the lambda x to the other side, and I wind up with a minus lambda times x plus by equals 0. And the other equation that I wind up with, if I manipulate this guy, move the lambda y to the other side, I wind up with cx plus d minus lambda times y equals 0. And you'll notice that this is another system of two equations, but we can now matricize this. And when we do that, we wind up with another equation that has kind of an interesting effect. And it looks like this. A minus lambda b c d minus lambda times x and y equals the 0 vector. Now remember, we want the special value, lambda, that makes this true. And here's why. Because if lambda is just magical and it makes this turn out to be the 0 vector, then that means this thing has a determinant of 0, right? That thing magically works out in our favor. So we want the special value, lambda, that makes this true, because that's going to give us the straight line solutions. And you're going to see how this works. We just need to recall a couple of things from last time. If you remember, the system of linear equations has a non-trivial solution, non-trivial, if and only if that determinant of the coefficient matrix is equal to 0. And so that means, in our case right here, we'd be saying the determinant of this guy right here, a minus lambda, b, c, d minus lambda, determinant of that thing equals 0. So we're going to set this thing equal to 0 and solve for lambda. And if you remember the determinant equation, we do this guy times this guy minus this guy times that guy. So that means we're looking at a minus lambda times quantity d minus lambda minus c times b equals 0. And what we're going to get is a quadratic equation in terms of this unknown lambda. This produces a quadratic, which is solvable for lambda. And so for our previous example, if you remember, we had a coefficient matrix. Our A matrix for the previous one was 2, 3, 0, negative 4. We've seen it so many times. We probably have it memorized. So for this particular system, we need to find the determinant of this thing, but with this modification of lambda here and here. So it would be 2 minus lambda, 3, 0, minus 4 minus lambda. So we got to set that determinant equal to 0, which, with a little bit of work, we can see is 2 minus lambda times minus 4 minus lambda minus 0 times 3 equals 0. And because this thing equals 0, it's kind of pre-factored for us. So there's two possibilities. One of them looks like this. Lambda equals 2. And the other one, right here, lambda equals negative 4. And those two values of lambda yield straight line solutions. Now, how they yield straight line solutions, we're going to show on the next page. So we'll leave that, or actually not the next page, but the 2 pages later. But we're going to leave off right here so you can ponder that, and we'll head into the next couple of pages where we're going to figure out how these values of lambda are really, really meaningful. They mean something for our straight line solutions.